Europe once faced a biological ceiling, a future where millions would starve, not for lack of land, but for lack of usable nitrogen. The air was 78% nitrogen, yet every farm was dying of hunger, locked out by chemistry. Then a process dismissed as alchemy, and even denounced as poison, fed 4 billion people and triggered a new planetary bargain. But what did it really take to transform nitrogen from a silent famine into the backbone of civilization? And what was the price? August 1898, a packed audience in Bristol listened as Sir William Crookes, one of Britain's most respected chemists, delivered a warning that echoed across continents. Crookes stood before the British Association for the Advancement of Science and laid out the numbers with cold precision. Wheat, he argued, was the foundation of civilization. But the very soil that fed Europe's growing cities was running out of the one ingredient it needed most: usable nitrogen. No amount of fresh land or harder labor could change this. Fields were starved of nutrients, and the best efforts of farmers, spreading manure, rotating crops, or planting clover, could not keep up with the demands of a swelling population. By the late 19th century, Britain and much of Europe had become dependent on shipments of Chilean saltpeter, a mineral nitrate mined from the deserts of South America. Every year, tens of thousands of tons crossed the Atlantic, packed into the holds of steamships, destined for both fertilizer and explosives. These nitrate deposits, ancient and finite, represented a lifeline. But Crookes knew the numbers. At the current rate of consumption, the world's known reserves would not last another generation. Without a new source, the wheat harvest would collapse, and millions would face hunger. Crookes did not couch his words in comfort. He described a future where, within decades, the demand for bread would outstrip all natural supplies. "It is a question of the not far distant future," he declared, "whether food production will keep pace with population." The audience understood what was at stake: a biological ceiling set not by the limits of land or labor, but by the chemistry of the soil itself. Crookes challenged the scientific world to solve what he called the greatest chemical problem of the age: how to extract nitrogen from the very air that enveloped every farm and city. He called on chemists to fix atmospheric nitrogen, turning an invisible gas into the lifeblood of crops. At the time, it sounded almost like science fiction. The air was thick with nitrogen, nearly 4 out of every 5 molecules, but locked away by chemistry, untouchable by plants or plow. Alternatives like guano, bone meal, and legume rotations had already been pushed to their limits. As Crookes spoke, the world's leading agronomists and industrialists were already scouring the globe for new nitrate deposits, but the supply was finite and the clock was ticking. The AIR that surrounded every farm was abundant, and yet useless. The sense of urgency. Crookes ignited did not fade. His warning transformed a quiet agricultural crisis into a global scientific race. The challenge was clear: unlock the nitrogen in the air, or face a future defined by scarcity and hunger. Chemists and engineers would spend the next decade searching for a way to break nature's most stubborn lock, knowing that the fate of millions depended on their success. Nitrogen gas fills the air above every field, making up nearly 78% of Earth's atmosphere. Yet, for all its abundance, this form of nitrogen is almost useless to crops. The reason lies at the heart of chemistry. Each nitrogen molecule is 2 atoms locked together by a triple bond, one of the strongest found in nature. Breaking that bond requires about 941 kilojoules of energy per mole, enough to keep atmospheric nitrogen inert, stable, and almost entirely unreactive under normal conditions. Plants cannot use nitrogen gas directly. they need it in forms like ammonium or nitrate, which dissolve in water and can be taken up by roots. But the process of turning molecular nitrogen from the air into these usable forms, known as nitrogen fixation, happens only in very specific ways. Lightning storms, with their bursts of energy, can split nitrogen molecules and create small amounts of nitrate that wash down in rain. Certain bacteria, living in the root nodules of legumes or free in the soil, can also fix nitrogen, converting it into compounds plants can use. Even with these natural processes, the total amount of nitrogen fixed each year is limited. Global biological fixation and lightning together add up to about 100 million to 200 million metric tons of nitrogen annually, spread thinly across the planet. For centuries, farmers tried to stretch this trickle of fixed nitrogen as far as it would go. They rotated crops, planted clover and beans, and spread as much manure as they could collect. But as the 19th century ended, these methods hit a wall. The world's population was growing faster than nature's ability to convert nitrogen into food. The paradox became clear. Humanity was surrounded by an ocean of nitrogen, but it was locked tight by chemistry, just out of reach. Scientists understood the challenge in stark physical terms. The nitrogen triple bond is so strong that it resists almost every attempt to break it under ordinary conditions. Laboratory demonstrations showed that even high heat or electricity could only force a tiny fraction of molecular nitrogen to react. Most chemists believed any artificial process would require more energy than it could ever return in crops. The dream of pulling fertilizer from thin air seemed as far-fetched as alchemy. Yet the urgency was real. Without a new way to fix nitrogen, the world faced a hard biological ceiling. Fields could not yield more, no matter how much land was tilled or how many hands worked the soil. The scientific problem was now defined. Find a way to break the nitrogen bond, to turn the most common gas on Earth into the rarest resource in agriculture. The quest for synthetic nitrogen fixation became the defining challenge for a generation of chemists and engineers. The solution would demand not just knowledge of biology, but mastery of physical chemistry, the ability to force the unreactive to react, and to do it on a scale large enough to feed nations. In July 1909, a cramped laboratory at the Technische Hochschule Karlsruhe became the unlikely stage for a chemical experiment that would change the world. Fritz Haber, a professor known for his restless ambition and single-minded focus, hovered over a glass and steel apparatus with his assistant, Robert Le Rossignol. The device looked fragile, with thin tubes, pressure gauges, and valves that creaked under strain. But inside, under conditions no farmer or chemist had ever dared attempt, something extraordinary was happening. Haber had spent years chasing a reaction most colleagues dismissed as fantasy. He believed that by forcing nitrogen and hydrogen together at extreme pressure and temperature, he could coax them into forming ammonia. The numbers were daunting. The system had to withstand nearly 200 atmospheres, pressure greater than found at the bottom of the ocean, and temperatures approaching 500 degrees Celsius. The catalyst, a precious layer of osmium, was chosen for its rare ability to tempt nitrogen's triple bond to break. For hours, the experiment ran, the team watching for leaks, ready to shut everything down at the first sign of danger. The risk was real. A misstep could mean an explosion, or at best, another failed attempt. But as the night wore on, a faint, sharp smell began to fill the lab. Drops of liquid condensed in a trap, unmistakable in their pungency. Ammonia, collected not from guano or Chilean nitrate, but conjured from the air itself. By dawn, the apparatus was producing ammonia in a steady stream, hundreds of grams per hour, enough to be weighed, measured, and confirmed. It was more than a laboratory curiosity. It was proof. The reaction was simple on paper. Nitrogen plus hydrogen yields ammonia. In practice, it had demanded a mastery of chemistry and engineering that few thought possible. Haber's notebooks from that night record the conditions: 200 atmospheres, 500 degrees Celsius, osmium catalyst. His colleagues, both awed and skeptical, called it alchemy, a magician's trick turning air and water gas into the foundation of bread. Some dismissed it as a laboratory stunt, elegant but useless on any meaningful scale. But for Haber, the experiment settled the question. The nitrogen in the air could be fixed. The lock had been picked. That night, as the first drops of laboratory ammonia pooled in the glass trap, the team celebrated with a bottle of wine. The sense of triumph was real, but so was the exhaustion. Le Rossignol later recalled the tension of monitoring valves and gauges through the early hours, knowing that any mistake could undo months of work. Haber, ever the pragmatist, was already thinking ahead. The science was proven, but the world's fields would not be fed by a few grams of ammonia in a glass tube. The next challenge loomed: to build machines that could do what the laboratory had done on a scale that could feed millions. In the eyes of many, the process still looked like alchemy. For Haber, it was the beginning of a new chemistry, one that would demand a new kind of industry. Carl Bosch arrived at BASF with a challenge that few engineers would have accepted. He had to transform a delicate laboratory reaction into a continuous industrial process capable of feeding nations. The path from Fritz Haber's glass tubes to a working factory was littered with broken steel, failed seals, and the ever-present threat of disaster. Every attempt to scale up the ammonia synthesis met the brute reality of high-pressure chemistry. The first prototypes cracked open, leaking hydrogen and ammonia, sometimes with enough force to blow steel apart like paper. Hydrogen, small and aggressive, wormed its way into the crystal structure of steel, turning vessels brittle and prone to sudden fracture. Each failure sent Bosch and his team back to the drawing board, searching for materials that could survive both the crushing pressure and the relentless attack of hot hydrogen. Bosch's solution was as much an act of metallurgy as of chemistry. He and his engineers designed reactors with layered walls, massive forged steel on the outside, soft iron liners inside, and sometimes powdered metal packed between. This composite approach allowed the vessel to absorb pressure, while sacrificial layers soaked up hydrogen, preventing it from reaching the vulnerable outer shell. The result was a pressure reactor unlike anything built before. Thick as a fortress wall, lined with iron, the design distributed stress so that no single flaw would bring catastrophe. These reactors were not just safe, they were overbuilt, with margins so wide that even the unknowns of long-term operation could not bring them down. At the heart of the process, Bosch's team replaced Haber's rare and costly osmium catalyst with a robust, promoted iron catalyst. Alwin Mittasch led a relentless campaign of testing, running thousands of experiments with iron ores and mineral promoters. By 1910, they had found a formula that not only matched osmium's performance but could be produced on an industrial scale. This single change transformed ammonia synthesis from a scientific curiosity into an economic reality. The engineering did not stop at the reactor walls. Compressors had to be invented from scratch, multi-stage machines with hardened conical valves, each stage cooled and lubricated to survive the pounding of high-pressure hydrogen. The entire system ran as a closed loop, nitrogen and hydrogen compressed, heated, passed over the iron catalyst, then cooled to condense out liquid ammonia, with unreacted gases recycled back through the system. This continuous loop, with its intricate network of pipes, heat exchangers, and control valves, was the first of its kind in chemical manufacturing. By September 1913, the Opal plant stood ready. Its towering reactors and humming compressors represented the fusion of chemistry and heavy industry. On opening day, the plant produced around 20 tons of ammonia, a daily output that dwarfed anything the world had seen. For the first time, atmospheric nitrogen was fixed not by the slow work of bacteria or the violence of lightning, but by machines. The success at Opal closed the era of laboratory-scale alchemy and opened the age of industrial nitrogen. Bosch's achievement was not just in making ammonia. It was in building the steel and steam infrastructure that made it possible to do so at scale, day after day. What began as a fragile experiment in a university lab had become the backbone of modern agriculture and soon became essential to war. When war broke out in 1914, the new ammonia plants in Germany faced a choice that would define the modern era. The British blockade cut off shipments of Chilean nitrate, severing the country's main supply of both fertilizer and explosives. Within months, the Haber-Bosch process, barely out of its infancy, was repurposed on a national scale. Ammonia, once hailed as a miracle for crops, now flowed into munitions factories. Nitric acid, produced from synthetic ammonia, became the backbone of explosives for artillery shells, bombs, and gunpowder. The same chemistry that promised to feed millions was now fueling a war that would claim millions of lives. Inside the war ministries and corporate boardrooms, the decision was blunt. Every ton of ammonia could be food or firepower, but not both. German officials coordinated with BASF and other firms to prioritize explosives, knowing that without synthetic nitrogen, the war effort would collapse within months. The process that had been dismissed as alchemy was now a state secret, guarded as tightly as any weapon. For Fritz Haber, this was a moment of national pride, but also personal cost. He was promoted for his contributions to the war, but at home the consequences were devastating. His wife, Clara Immerwahr, a chemist in her own right, and one of the first German women to earn a doctorate in chemistry, watched in horror as the science she loved became an instrument of death. In May 1915, just days after Haber returned from overseeing the first chlorine gas attack on the Western Front, Clara took her own life. Some accounts describe her suicide as a final protest against the weaponization of chemistry, a tragedy that haunted Haber for the rest of his life. In these years, the promise and peril of synthetic nitrogen became inseparable, binding the fate of food, war, and conscience. Today, nearly half of all the food grown on Earth owes its existence to synthetic nitrogen. Scientists estimate that 40 to 50% of the world's food production now depends on ammonia made through the Haber-Bosch process. That is not just a statistic. It means about 4 billion people are alive because of a chemical reaction that pulls nitrogen from the air and turns it into fertilizer. Factories around the globe now produce 200 million metric tons of ammonia every year, most of it destined for fields of wheat, rice, and corn. But the same process that shattered the old biological ceiling has created new pressures on the planet. Far more nitrogen is applied to farmland than crops can absorb. The excess runs off into rivers and streams, traveling hundreds of miles before reaching the sea. In the Gulf of Mexico, this runoff feeds an annual dead zone that can stretch over 6,000 square miles, an area larger than the state of Connecticut, where oxygen levels drop so low that fish and shellfish cannot survive. The problem does not stop at water. In fields and soils, microbes convert some of the surplus nitrogen into nitrous oxide, a greenhouse gas nearly 300 times more potent than carbon dioxide over a century. Agriculture now accounts for about 80% of all human-caused nitrous oxide emissions. The same chemistry that feeds billions is now reshaping the air, water, and climate, leaving humanity with a planetary bill that grows every year. Half of humanity now relies on nitrogen conjured from the air, and every year 200 million tons reshape our climate and our waterways. As demands for food and population keep rising, the balance between sustenance and survival grows more precarious. Modern civilization is not just built on steel or silicon. It is built on chemistry we can no longer live without. The world we inherit depends on how we manage it next. Share your thoughts below.